All right, in this video, we're going to go over how to deal with collisions using a strategy called chaining. So with chaining, it's not too bad. So most people don't find this strategy too confusing, but basically your hash table, that array that you set up, instead of it being an array of structs or an array of specific data, it's just going to be an array of pointers or an array of linked lists where each element in the array is like the head node to another linked list, right? It really could be an array of any other kind of data structure too. So you could think of it as an array of trees where, each element in the array is the root node to a tree. It could also even be an array of other hash tables. So all that's important is that you now have a hash table that isn't a single value in each element. And so when you insert into the link into the hash table now, you're going to insert it into the proper linked list along the array. So let's say that we have this hash table, and so the values that you're seeing here in orange, those are just the indexes of the array. And let's say that we do a hash and we find that this UIN needs to go into the location 45,678. So what you're going to do is create a node, fill it with that key, and it's important that you actually keep the key now because the key is going to be needed in order to determine which node in the linked list matches the key that was passed in. And then you place the student data there. So if you hash in another UIN and it happens to hash to the same value 45,678, then you're just going to link that student node off of the one that's already there. And so now anytime you need to look up student data for either of these UINs, the UINs will both point you to this right location in the hash table, but then you're going to have to search the linked list that the hash table is linking you to. So let's look at what this code looks like a little bit. So we're going to need to have a struct that keeps track of now the key, the value, and the next node. So it's very similar to a linked list or a tree struct. You just have the data in there and then any pointers that you need. So when we create our array is going to be an array of struct pointers, right? So we're not creating an array of structs, but we're creating an array of pointers that point to structs, right? So the syntax for that is to include the pointer in the declaration here. If you aren't using the square bracket notation, that would mean that the pointer table that you're creating, so table is an array, but it's also a pointer to the front of the list, to the front of the array. That pointer is now a pointer to a pointer, so you have a double star. And if you think that's just totally blowing your mind that you could have 2 pointers, you could even have 3. You could even have 4. So it just means that it's a pointer pointing to a pointer. And that's because this array that we've created, table, that points to the front of an array of pointers. And so its table is a pointer to a pointer. Okay. Enough of that. So what we'll do is we'll go ahead and start off by just initializing all of these pointers to null pointer. Just a great habit to get into the habit of doing. So we're just going through and setting all of those struct pointers to null pointer. So continuing on, how does this work? So let's try to insert a key value pair into our hash table. So assuming we have a key and a value, the first step is to hash just like normal and get the index. Then what you're going to do is you are going to create a new node. So your new node is going to have the key that you put in, it's going to have the value, and then it's going to have the next pointer. And so what we're going to do is we're just going to go ahead and point that to whatever is currently in the table, and then update the pointer that's in the table to the front of the list. And so what that will do is it will always insert the node in the front of the list. There's really no benefit to inserting at the front or inserting at the back. The example I showed before inserted the node at the back of the linked list. I'm sure you've thought about this in past projects where we've done a bunch of link structures, but you're either inserting at the front and then having to walk through it to get to the back, or you're inserting at the back and having to walk through it to get to the front. So you just have to really decide whether you'd rather pay the cost of inserting and walking the list, or searching and walking the list. But yeah, so that's all chaining is. There's really not much more to it. As I said before, this array could be an array of any kind of data structure. So you could also, instead of putting linked lists in the element locations here, you could just do root nodes to trees, and then obviously that would improve your efficiency because you would be able to search each individual element. So like when you hashed and you got the index, the complexity of then having to search that index would be then log n, right? Where n is the number of elements that are duplicated or that collide in that location. So that can also help, is having hash tables that have other structures behind them. And then, as I said, you could just put all of these as hash tables as well, so that they that each of these points to another array that is in itself a hash table, which would improve efficiency but increase complexity of writing the code. All right, so that is it for chaining.